So let's look at an example of applying Gauss's law to a symmetric situation. And you really only want to use it when you've got symmetry and uniformity. Symmetry and uniformity. So let's say we're trying to find the electric field outside of a charged sphere that's uniformly charged and has a total charge little q. Let's do that here. So let's say we've got this sphere. It's a sphere of charge, and it's got total charge little q, and it's uniformly charged. Now, since this is a nice symmetric situation, it's spherically symmetric, I'm going to draw a Gaussian sphere. So I choose to draw this imaginary surface around the charge. And I know that the field of this charge is going to be outwards, and so E is pointed in every direction out, radially outwards. I also define my dA as the surface, as the differential that points normal to the surface. So dA here, let's draw it in a different color. Here's dA. It's normal to the surface. So dA is normal to the surface there. Same thing here. So it's like all of these little lines pointed in the same direction. Notice that they are parallel to E. That's why I've chosen this Gaussian surface in the first place, because it's a nice choice. It satisfies condition number 1. So now condition number 1 is satisfied, and the dot product has basically just become the two magnitudes multiplied together. Now I also know that each of these places where E intersects the Gaussian surface will be the same value of E. So E is not going to be any stronger here than it would be here versus here, or any place where E intersects the Gaussian surface. So E is constant over the surface, dA. That means that I can take E outside the integral, so I've done that here. Okay, now I've got E, and I need the area of the Gaussian surface. I know the charge enclosed, it's going to be little q, and that's a constant. So now I can apply Gauss's law. It's going to be E, let's write it over here, the magnitude E times the surface area of the Gaussian surface. Now let's say I define that with radius little r. That's not the radius of the sphere, it's the radius of the Gaussian surface, because that's where I want E, times 4 pi little r squared equals q enclosed. Oh, and I know q enclosed. That's q over epsilon naught. So now we've applied Gauss's law, and we simply solve for the electric field and the magnitude of the electric field. And that looks like E equals, I'm going to rearrange it so that you recognize Coulomb's law, or I'm sorry, Coulomb's constant, 4 pi epsilon naught, 1 over 4 pi epsilon naught, r squared on the bottom. And notice that it looks a lot like the electric field due to a point charge.